Welcome to QHSE Talks, the show where we explore the real stories, systems, and science behind workplace safety. And today, we're kicking off our Basic Safety series, a journey back to the fundamentals where safety begins. In this very first episode, we're talking about one of the most powerful ideas in the safety world, that safety is both a science and an art. The science is what most people see first. The numbers, the calculations, the engineering controls, the checklists, the data. It's the part that can be measured, designed, and tested. But what we often forget is the other half, the art. The art of safety is about people, their behaviors, their intuition, their leadership, and the choices they make every day on the job. Because no matter how perfect a safety procedure looks on paper, it only works when people believe in it and follow it. So in this episode, we'll explore how those two sides, science and art, come together to form the foundation of every strong safety culture. We'll also unpack how hazards and exposure lead to accidents, how we analyze root causes, and why prevention always starts with understanding. So, let's get started with the basics, the real balance between science, systems, and human nature that defines what safety truly means.
Well, I think it's a really smart way to start, actually, because it admits right off the bat that engineering controls alone aren't enough. The science part, that's the tangible stuff.
Like the calculations, the standards?
Exactly. Data analysis, engineering principles, API standards, ESME codes, physical barriers, analyzing incident statistics. It's all about trying to get objective, reliable designs. Predictable.
Okay, so that's the hard science. Where does the art come in? Feels a bit soft for this industry.
It is the softer side, but it's absolutely critical. The art is, well, it's the human element. It's the safety culture on site. It's the leadership style. It's how employees actually behave, maybe even their intuition about things. It's what makes the science stick.
Ah, I see. So you can have the perfect procedure.
The perfect lockout procedure, let's say. That's the science. But if the culture, the art, allows people to take shortcuts, maybe because nothing's gone wrong yet. Sociologists call it the normalization of deviance.
Right. Everyone starts bending the rules just a little bit.
And suddenly, that perfect scientific control is basically useless. The failure isn't the engineering, it's the culture letting standards slip. The art is about leadership, vigilance, fighting complacency, no matter how solid the science looks.
That's a really important frame. Okay, so understanding safety involves both. How do we then understand failure?
Yeah.
The sources dive into accident causation.
Right. To prevent failure, you have to understand how it happens. The model here breaks it down into like 4 key pieces that interact. You need some kind of release that's either energy or a chemical.
Okay, the hazard itself escaping.
Yeah. And that release happens because of a failure in control, which they categorize as either an unsafe act or an unsafe condition.
Let's unpack those a bit. Release, energy, or chemical. Energy could be pressure.
Dropped objects. Yeah.
Pressure vessel burst, that's stored energy. Dropped load from a crane, potential energy released. Electrical arc flash. Chemical release is maybe more obvious. A leak, a spill, a rupture.
Right.
That's the physical event.
Got it. And that event is allowed to happen by either an unsafe act or an unsafe condition. Correct. You can't stop there. The unsafe act is the human factor, the behavior. Someone operating equipment they aren't trained for, maybe removing a guard, skipping a vital step in a procedure. And the unsafe condition is more about the environment or the equipment itself. Purely maintained gear, maybe inadequate lighting, a corroded pipe, faulty design. Basically, the system sets you up for failure.
So an accident needs both, the hazard release and the act or condition that lets it happen.
Well, it often needs that alignment, yeah. The unsafe act or condition creates the pathway for the energy or chemical release to actually cause harm to people or equipment.
And investigating isn't just about finding that immediate cause, is it? That brings us to root cause analysis, or RCA.
RCA.
Yeah.
Super important. It's about getting past the blame game and looking at the whole system. It sets up this kind of hierarchy of causes. Let's use an example. Say a worker gets burned by steam from a pipe.
Okay. So the direct cause is obvious. The steam release caused the burn.
Yep. Immediate, observable. Now, you ask why. Why did the steam release unexpectedly? Maybe you find a valve failed. That takes you down a level to the indirect causes.
The things that allowed the valve to fail.
Exactly. Maybe the maintenance schedule for that valve was missed. That's an indirect cause failure of the maintenance system. Or maybe the worker wasn't trained on the right way to isolate that line. failure of the training system.
But if you just stop there and say bad maintenance or needs more training,
You might fix that valve or train that worker, but you haven't fixed the underlying reason why maintenance gets skipped or training is inadequate. You need to dig deeper for the root cause.
which is usually more systemic,
Yeah.
management level.
Almost always, yeah. It often comes back to management systems, policies, budgets, or the overall culture. So if maintenance was skipped, was the root cause maybe a budget policy that delays spending on preventative work? Or a culture where production targets always trump maintenance needs?
Ah, okay, so you have to fix that deeper issue, the decision-making process, or the problem will just pop up somewhere else.
Precisely. Otherwise, you're just putting Band-Aids on things.
This whole structured approach, this proactive thinking, seems to define what the sources call the company safety program. It's laid out as a cycle. 3 steps, 3 questions.
Yeah, it's this sort of operational philosophy. It organizes everything. Starts with step 1, identify hazard. Simple question. What can go wrong?
Just listing out all the potential bad stuff. Toxic gas, falling objects, high pressure.
Everything. Once you know the threats, you move to step 2. Use safe practice. Which answers? How do you prevent it? And this is where your prevention barriers come in.
Okay, prevention barriers. These are proactive, things you do before anything goes wrong.
Exactly. Designed to stop the incident happening in the first place. Think engineering controls pressure relief valves, safety interlocks, or administrative controls work permits, procedures, training. These are upstream defenses, aiming for 0 incidents, 0 releases.
But realistically, things can still go wrong. So, step 3, plan for emergencies. The but what if question.
Right. And that requires protection barriers.
Yeah.
These are reactive measures. They kick in after something has failed to limit the damage.
Like,
Emergency shutdown systems, the big red button, fire suppression, like sprinklers or deluge systems, containment walls or dikes around tanks, blast-resistant control rooms, the whole emergency response plan itself, evacuation procedures, all that. It's the combination prevention and protection that makes a system resilient.
and the best way to picture these layers failing is the Swiss cheese model. It comes up a few times in the material.
Oh yeah, it's classic. A really powerful visual for explaining systemic failure. It pictures your safety system as, well, slices of Swiss cheese.
Each slice is a barrier, like training or procedures or hardware.
Yep. Design review, operator training, warning alarms, physical guards, maintenance checks. Each one is a slice, ideally solid slices. But reality isn't perfect. Each slice has weaknesses or holes. These could be latent conditions like a design flaw, or active failures like someone making a mistake.
And the catastrophe happens only when the holes in several slices line up for a moment.
That's the key insight. It's almost never a single failure. Think about a major disaster. You might have a hole in the management decision slice due to budget cuts. Then another hole in procedures because a step was skipped. Then a hole in equipment because a sensor failed.
And the hazard just passes straight through all those aligned holes.
Exactly. It forces you to see safety as a whole system. You can't rely on any single barrier being perfect. It's the depth and integrity of all the layers together that counts.
Okay, that model makes a lot of sense. Let's dig into the specific hazards then. In-depth hazard identification. The sources list quite a few beyond just fire.
You do. And you have to be systematic. Obviously, hydrocarbons, HC, crude oil, natural gas, refined products, they're central because they're flammable, sometimes toxic. But the list goes way beyond that. You've got a whole range of energy hazards.
Electrical, obviously.
Mechanical. Yep. Rotating equipment, moving parts. Potential energy, things that can fall, like suspended loads or even workers at height. Pressure energy is stored in vessels or pipelines. Heat, radiation. Tate.
It's a broad category. The pressure one seems particularly relevant. It's not just the substance leaking, but the force behind it.
Absolutely. A high-pressure gas release isn't just a potential fire. It can be like a jet engine, causing massive physical damage or turning debris into projectiles. Then you have things like noise and vibration. Maybe not instantly catastrophic, but they cause long-term harm, fatigue, communication issues, equipment damage.
Right. And then there's the detailed section on gases. This really shows the chemical complexity. It's like a menu of different ways a gas can hurt you.
It is, and you need to know the specific threat each gas poses. They list toxic gases, H2S, hydrogen sulfide is the classic example. Nasty stuff. Knocks out your sense of smell right before it incapacitates you.
Scary. Then suffocation inert gases.
Like nitrogen or argon.
Yeah.
They just push out the oxygen in the air. You can breathe them in and not even realize you're suffocating until it's too late.
Yeah.
No warning signs.
Okay, what else?
You've got corrosive gases that damage tissue and materials. Pressurized gas is the physical hazard again. Flammable explosive, obviously a huge concern. Then some others. Irritant gases, oxidizers,
Oxidizers, they make fires worse.
dramatically worse. They provide extra oxygen, making fires burn hotter and faster. Think pure oxygen or chlorine. Then cryogenic gases or liquids like LNG. Extreme cold is a hazard freeze burns, making metals brittle. And finally, reactive gases that can decompose violently or explode under certain conditions.
Wow, that's a lot of different dangers from just gas. How do people know what they're dealing with quickly?
That's where things like the hazardous materials placards come in, the diamond-shaped signs with numbers and colors you see on trucks and tanks. They give first responders and workers immediate visual cues about the main dangers of flammability, health, reactivity. It's a standardized system.
Okay, so we've identified all these hazards, but the sources stress that a hazard alone isn't an accident. You need exposure.
Right. Exposure is the crucial link. A hazard only becomes an actual risk or leads to an accident when people or assets are exposed to it. You could have a highly toxic chemical securely contain massive hazard, but zero exposure. So zero immediate risk.
So exposure means being in the danger zone.
That's the definition used, yeah.
Yeah.
Someone or something valuable is within the range where the hazard can cause harm.
And they distinguish physical exposure from environmental exposure. What's the difference there?
Good question. Physical exposure is generally close range, direct contact, like putting your hand near a moving part or being directly in the path of a potential spray or projectile. You manage that with guards, keeping distance, personal protective equipment, PPE.
Okay. And environmental.
Environmental exposure is more widespread, affecting a whole area. Think high noise levels across a plant floor, or a hazardous atmosphere like toxic fumes or lack of oxygen that permeates a space. It affects everyone in that environment.
And managing that requires different controls, right? Not just PPE, but maybe ventilation systems, area monitoring, facility-wide alarms.
Exactly. It shifts from individual protection to engineering and administrative controls for the whole area, but the basic equation always holds. Hazard plus exposure, it's accident. If you can break that chain by removing the hazard or preventing the exposure, you prevent the accident. And often, controlling exposure is the more practical, immediate step.
Okay, hazard plus exposure equals accident. That leads us neatly into risk. The risk management framework, it's defined by two things: consequence and likelihood.
That's the core idea. Risk isn't just about how bad something could be, it's about how bad it could be and how likely it is to happen. So, consequence severity, is it minor, serious, major, catastrophic? And relative frequency of occurrence likelihood, is it frequent, occasional, rare, improbable?
And you manage those differently, a common small cut versus a rare plant explosion.
Precisely. You might accept more frequent minor risks, like small cuts managed with first aid and gloves, but you need incredibly robust controls for those low-frequency, high-consequence events, the potential catastrophes that define O&G process safety.
The framework itself is a four-step process.
Yeah, a logical sequence. Step one is hazard identification, which we've talked about. Then risk analysis, that's where you try to figure out the actual likelihood and consequence using data, models, experience.
Okay.
Then comes risk assessment. This is the judgment step. You compare the analyzed risk against your criteria, company standards, regulatory limits like OSHA regulations, societal tolerance. Is this level of risk acceptable, or does it need to be reduced?
That sounds like the hard part. Deciding what's acceptable, especially for potentially catastrophic events.
It is hard. It involves ethics, public perception, economics, not just pure science. Often for major hazard, you'll do a detailed quantitative risk assessment, QRA, to get actual numbers like the probability of a fatality per year. Then the final step is risk management, implementing the controls needed to reduce the risk to an acceptable level or as low as reasonably practicable. ALRP. And underpinning all of this is robust emergency preparedness for when controls fail.
This focus on major events brings up another key distinction: process safety versus personal safety. This seems really fundamental.
Absolutely fundamental. This is probably one of the biggest conceptual shifts in safety management over the last few decades, driven by major accidents. Personal safety is what most people think of first, preventing injuries to individuals: slips, trips, falls, cuts, strains, things that happen relatively often, but usually have lower consequences for the facility as a whole.
And the metrics we often hear about, like TRAR, total recordable incident rate, mostly track personal safety, right?
Mostly, yes. And you can have a fantastic personal safety record, very low TRAR, and still be moments away from a catastrophic process safety failure. They don't always correlate.
So what defines process safety then?
Process safety is all about preventing catastrophic events. specifically preventing the unplanned, uncontrolled release of hazardous materials or energy. We're talking major fires, explosions, toxic releases that could impact the facility, the environment, and the public outside the fence line. Low frequency, high consequence.
So a worker falling off a ladder is personal safety. A pipeline rupture leading to a massive fire is process safety.
Exactly. And the source material also mentions that it's sometimes hard to neatly separate energy and chemical hazards in these events.
How so?
Well, think about it. A flammable chemical leaks, chemical hazard, because the vessel it was in failed due to overpressure, energy hazard. The release itself might be driven by pressure energy, and then it ignites. They're often intertwined in process safety incidents.
Okay. Managing both kinds requires a real commitment to loss prevention across the board, doesn't it? Not just a safety department job.
Definitely not. It has to be embedded everywhere. Top management has to genuinely commit, provide resources, set the safety culture tone. Managers and supervisors have to implement the policies, make sure procedures are followed, ensure people have the right tools and training. And employees need to be engaged, follow the rules, speak up about hazards.
And it's about managing more than just the hazards themselves.
Right. The sources list 5 things to manage.
Yeah.
The hazards, yes, but also the employees, their training, behavior, the material being handled, its properties, condition, the equipment, its design, maintenance, integrity, and the surrounding environment. Neglect any one of those, and you create vulnerability.
So how do companies actually do this systematically, especially for complex processes? That's where the process hazard analysis, PHA methods, come in.
Correct. PHAs are the formal, structured ways companies examine their processes to find potential weaknesses or ways things could go wrong, deviations from the intended design or operation that could lead to a release.
And there are different levels of detail, qualitative, quantitative.
Yeah, we classify them roughly by how precise the risk estimation is. Qualitative Q methods might just categorize risks as low, medium, high. Simple, good for initial screening. Semi-quantitative Q methods use scoring systems or risk matrices to get a bit more definition, maybe putting risks into specific ranges.
And
Quantitative risk assessment, QRA, is the most detailed. It uses failure rate data, consequence modeling software, fault trees, event trees, to calculate actual numerical risk levels, like probabilities of failure or fatality rates. You'd use that for your highest risk scenarios.
Okay. And the specific tools used depend on what you're trying to achieve, like looking back versus looking forward.
Exactly. If you're trying to understand historical context, learn from the past, you'd use root cause analysis on previous incidents, review lessons learned, talk to experienced personnel.
Makes sense. What about analyzing a plant that's already running, existing conditions?
For that, you've got a toolbox of systematic methods. A checklist is the simplest, comparing against known standards or common hazards. What if analysis is more of a brainstorming technique, asking what if this happens for various scenarios.
But the really rigorous ones for complex processes are things like HAZOP, right? Hazard and operability study. How does that work? Sounds intense.
It is intense, but very thorough. A HAZOP team takes a process diagram, breaks it down into sections or nodes, and then systematically applies guide words to process parameters at each node.
Guide words.
Like words like no, more, less, reverse, as well as part of. You apply these to parameters like flow, pressure, temperature. So at a specific point, the team asks, what if there is no flow? Or what if there is more pressure? Or what if there is reverse flow?
Ah, okay. And for each deviation, they figure out the causes, consequences, and existing safeguards.
Exactly. It's a very structured way to brainstorm potential problems and make sure nothing gets missed. It requires a multidisciplinary team operations, engineering, maintenance, safety.
Okay, what about FMEA and FTA? Failure modes and effects analysis and fault tree analysis.
Right. FEA tends to be more equipment-focused. You look at the specific component like a pump or a valve and ask, how can it fail? That's the failure mode, like fails to open, leaks externally, stuck closed. Then you figure out the effect or consequence of that failure on the system. You often rank these by severity, likelihood, and detectability to prioritize action.
And fault tree analysis, FTA.
FTA works the other way around. It starts with an undesirable top event, something you really want to prevent, like tank overfills or vessel explosion. Then you work downwards, identifying all the combinations of equipment failures, human errors, and external events that would have to occur to cause that top event. It maps out the failure logic, often using A&E gates and OR gates.
So it shows you all the pathways to disaster.
Pretty much, yeah. Helps you identify critical components or single points of failure.
And lastly, what about when you change something? Introducing new equipment or procedures.
That's where management of change MOC comes in. Hugely important. MOC is a formal process that says any change, not just big ones, even small ones like changing a type of gasket or tweaking a procedure, must be reviewed for its potential safety impact before it's implemented.
So it forces a mini PHA before you make the change.
Essentially, yes.
Yeah.
The MOC process makes you ask, does this change introduce new hazards? Does it affect existing risks? Does it impact existing safeguards? Often you'll need to do a what-if or maybe even a HAZV or FMEA specifically for the proposed change before it gets approved.
Yep.
It prevents unintended consequences.
Okay, that covers the process and system side really well. Let's shift gears a bit to the actual chemistry, especially fire. Fire chemistry fundamentals. It starts with the classic fire triangle, right?
Yep, the absolute basics. Fire needs three things to start. You need fuel, something that can burn, a combustible or flammable material. You need oxygen, usually just from the air, but could be a chemical oxidizer. And you need heat, an ignition source hot enough to get the reaction going.
Take away any one of those legs. Fuel, oxygen, or heat, and the fire goes out. Cool it, smother it, remove the fuel.
Exactly. That's the basis of most traditional firefighting.
But then the sources bring in the fire tetrahedron, adding a fourth element.
Right. The triangle explains ignition, but for fire to keep burning, to be self-sustaining, you really need that fourth element, the chemical chain reaction.
What's that exactly?
It's the process within the flame itself. Burning produces highly reactive molecules called free radicals. These radicals then react further, producing more heat and more radicals, which break down more fuel into vapor, which burns, creating more heat and radicals. It's a continuous cycle.
And why is adding that fourth side important for safety folks?
Because it gives us another way to stop the fire. Water removes heat. Foam or CO2 removes oxygen, smothering. But some modern extinguishing agents, especially some of the cleaner ones replacing halon, work primarily by interrupting that chemical chain reaction. They scavenge the free radicals, breaking the cycle, even if there's still fuel and oxygen present.
Ah, interesting. So it offers a different mechanism for specialized systems.
Precisely. Understanding the tetrahedron helps explain how different agents work.
Okay. Now, speaking of fuel, there's a really critical distinction made between flammables versus combustibles. It all hinges on one specific temperature, doesn't it?
It does, and this is a definition you absolutely have to know in this industry because it has huge regulatory consequences. The difference boils down to the ability to produce ignitable vapors at normal temperatures.
How easily does it give off enough fumes to catch fire?
Basically, yes. It's related to vapor pressure and flash point. And the dividing line, the magic number used in most regulations like NFPA and OSHA, is 37.8 degrees Celsius, which is 100 degrees Fahrenheit.
Okay, 37.8 C or 100 F, so below that temperature.
If a liquid gives off enough vapor to form an ignitable mixture with air below 37.8 C, it's classified as flammable. Think gasoline, acetone, ethanol. They can easily ignite at room temperature or even colder. They're inherently dangerous because an ignition source is often all that's needed.
And if its flash point is at or above 37.8 C?
Then it's classified as combustible. Think diesel fuel, heating oil, motor oil. These liquids need to be heated above 37.8 C before they produce enough vapor to ignite. Solids that burn are generally also considered combustible.
So the risk profile is different. Flammables are dangerous at ambient temperatures. Combustibles generally need heating first.
That's the key practical difference. And that classification dictates everything: how you store it, handle it, the type of electrical equipment you can use nearby, explosion-proof ratings, ventilation needs, fire protection requirements. It's a fundamental safety distinction based entirely on that 100-degree F threshold.
Let's apply this to a specific substance, natural gas. The sources describe it simply as a naturally occurring hydrocarbon mix.
Yep, primarily methane, CH4, but can have other hydrocarbons like ethane, propane, butane, plus impurities. It's a fossil fuel, obviously huge for heating and generating electricity because it burns cleaner than coal or oil.
But it's also used for other things.
Oh yeah, massively important as a chemical feedstock. It's the starting material for making plastics, fertilizers, pharmaceuticals, solvents, fabrics, all sorts of things. And as the source notes, increasingly used as vehicle fuel too, often in liquefied form, LNG, or compressed form, CNG.
And it can exist in different states, which affects safety. Liquid, gaseous, solid.
Right. Normally it's a gas. Under high pressure in pipelines, it's a dense gas. Cool it down to about -162 Celsius, and it becomes a liquid LNG, which is much denser, making it economical to transport by ship. But handling LNG brings cryogenic hazards, potential for brittle fracture of equipment, and the risk of large, cold, potentially flammable vapor clouds if spilled.
Solid. How does natural gas become solid?
Under certain conditions of low temperature and high pressure, especially in the presence of water, it can form ice-like solids called hydrates. These can actually plug up pipelines, which is a significant operational problem and potential hazard.
Interesting. Okay, one last piece on the chemistry. The combustion equation and the need for energy and mass balance. This sounds like engineering calculation territory.
It is. This is about being able to predict what happens in a fire or explosion scenario. The combustion equation is just the balanced chemical reaction showing the fuel reacting with oxygen to produce combustion products, typically CO2 and water, plus heat.
Like Chemistry 101, balancing the atoms.
Pretty much. CH4 plus 2O2 match the CO2 plus 2H2O. You need to ensure mass balance, that the mass of reactants equals the mass of products. And crucially, energy balance accounting for the heat released by the reaction.
Why is calculating that heat release so important for safety?
Because it tells you the intensity of the fire, how much heat energy is being radiated. This determines the potential impact on surroundings. Different fire types, a pool fire from spilled liquid, a jet fire from a pressurized leak, a flash fire through a vapor cloud, have very different heat outputs and radiation footprints.
So engineers use these calculations to figure out safe separation distances, how far away equipment or people need to be, or how much fireproofing is needed.
It's exactly. Calculating the heat flux based on energy and mass balance allows you to design protective measures. Insulation, water curtains, setting exclusion zones, designing blast walls. It's the quantitative basis for fire protection engineering.
Okay, we've covered a huge amount of ground there. Let's try to wrap this up.
Yeah, it's been a real deep dive.
We've gone from the philosophy of safety that science and art blend through the structures for understanding failure, like root cause analysis and the brilliant Swiss cheese model. We detailed the sheer variety of hazards, especially around energy and gases.
And clarified that vital difference between personal safety's focus on individual injuries and process safety's focus on preventing those low-frequency, high-consequence catastrophes. We looked at the tools used for analysis, HAZO, FMEA, MOC, and the fundamental fire chemistry, including that critical 100-degree F-line for flammables.
It really drives home that safety isn't luck. It's a highly structured, layered system designed to anticipate and contain failures. The goal is to prevent those holes in the cheese from ever lining up.
And remember where we started that art piece? The human factor is woven through all those layers. The models account for procedures not being followed, for decisions made under pressure.
Which leads perfectly into a final thought for you, the listener, to maybe mull over. We established the formula: hazard plus exposure, accident. And we know unsafe acts are a major contributor. So thinking about yourself, on site, surrounded by well-engineered systems, what's the one part of that equation you have the most direct personal control over?
Right. You might not be able to eliminate the hazard easily, but what about the exposure? How much does your personal choice to follow the procedure exactly, to stop the job as something feels wrong, to question an unsafe condition, how much does that choice directly control your exposure and therefore your risk? It puts the art of safety, that individual commitment, right back at the center, doesn't it? It's maybe the last and most flexible line of defense.